All right, chemistry students, welcome back. Apparently you have picked video number 2, which is the concrete rules for determining sig figs. Congratulations, you right-brained people and your silly, silly rules. Here we go. What will follow will be 6 concrete rules to help you determine the number of sig figs in any given value. Feel free to get these tattooed on your body someplace. Maybe right next to that I love chemistry tattoo that you don't tell your friends about. Here we go. The first rule, non-zero integers are always significant. Basically, any number other than 0 is going to be considered to be significant. That's an easy one. So for example, 46.3 has 3 sig figs because each of these is a real number. 6.295 grams is going to have 4 sig figs because all non-zero integers there, 4 sig figs total. Rule number 2, a 0 between non-zero digits is significant. All right, you could say a 0 that is sandwiched between 2 real numbers will be significant. So in this case right here, the 40.7, that 0 is considered to be significant because it is sandwiched between 2 real numbers, giving us 3 total sig figs. And this number right here, we have a real number here, a real number here, which means the 2 zeros in between will be considered to be significant. So we have 1, 2, 3, 4, 5 sig figs. Here we go. Rule number 3, a 0 in front of non-zero digits are not significant. A 0 in front of non-zero digits are not significant. For example, if we were measuring this value here, the 9, the 5, the 8, and the 7 are considered to be significant. This 0, this one, and this one are mere placeholders. They're just guys holding your place in line, right? They don't actually indicate the accuracy or the precision of the number. They're just placeholders. Same situation here. These zeros are going to be placeholders because they are in front of a non-zero digit. So here's a non-zero digit. They're in front of it, so they are not significant. Doesn't matter, doesn't matter, doesn't matter, doesn't matter. The 9 is the only significant one, 1 sig fig in that number right there. These are all placeholders. Okay? Feeling good about that? Let's move on to number 4. Number 4, zeros at the end of a number and to the right of a decimal place are significant. So here we are. We have the end of a number, but they are to the right of a decimal point. Okay, we're going to talk about the other example here later. Just realize that these two are going to be after a decimal point and at the end of a number. So they are considered to be significant. If you get confused on this one, imagine yourself weighing something. If you were in chemistry class right now and you weighed something and the scale came up and said 85.00 grams, those 2 zeros are indicating an accuracy and precision there, right? Those are actual real measured values. It just happened to be exactly 85.00. Okay, they are significant. They're not placeholders here. They're actually indicating a precision. Same situation here. Let's say if we went with our scale example, you would have a ridiculously accurate scale. That would mean that your number just happened to equal out to exactly this. Okay, so these are significant. They are not placeholders. Okay, they're not placeholders. 10 sig figs in this number. Number 5. If you have a decimal point after the zeros, it indicates that the zeros are significant. This is a tricky one because this means from this point on, whenever you do math, the decision to put a decimal point after your number is now a decision that you have to make on purpose because it is an indicator of how many sig figs you have. For instance, if I write 2000 with a decimal point, these zeros in between here that are sandwiched between my decimal point and my real number are significant, 4 sig figs. Whereas here, without a decimal, I have only 1 sig fig because they're not sandwiched in between that decimal. Only the 2 is going to apply as a sig fig. So now, whenever you do math and you get an answer, you have to stop and think, should I put the decimal point here? Because it will change the number of sig figs that you'll be indicating. Number 6. Now this was mentioned briefly when we went through the PowerPoint on how to do scientific notation, but you may not have picked it up. Scientific notation has 2 uses. The first, obvious one, is that it's a method for writing extremely large or small numbers. Really, really big numbers. I don't got time to write out 23 zeros. It's just not going to happen. I got things to do. So instead we use scientific notation. It's much, much faster. What you may have missed is that scientific notation is also a convenient way to indicate the precision or sig figs of a number. For instance, let's say we're doing some math, right? And our 2 numbers that we measure come out and it tells us that our answer needs to be rounded. Don't worry about why this happens. We'll talk about it in the next video. Let's just say we need to round our number to 2 sig figs. Okay, well, round 7,000 to 2 sig figs. Go ahead, try it. Okay, now if you just thought in your head that 7,000 rounds down to 70, you should poke yourself in the eye, because that makes no sense at all, right? In what world is 7,000 ever going to round to 70? Does 70 have 2 sig figs? Sure it does. But it is not the same as 7,000. You need to remember, we need our values to be equal here, or rounded at best, not completely different like 70 and 7,000. The correct way of doing this is to actually use scientific notation. If I convert 7,000 into scientific notation, I can write it like this. 7,000 times 10 to the third. Right here I am indicating that I have 2 sig figs, right? 2 sig figs. I have a 0 after a decimal point and a real non-zero number, so 2 sig figs in my answer. If I converted it back out, it would be equal to 7,000. So I have not changed the number entirely. I've just written it in a different way to indicate my precision. This will happen not a lot, but enough that it's important to know. Let's try another one. Let's say we do some math and we get this answer right here. Now, our math tells me that we should round our final answer to 3 sig figs. Go ahead and think to yourself, see if you can answer that. 3 sig figs. What should our final answer be? Okay. Now, if you just went through and rounded this number to 180, that's not going to happen. Not going to be equal at all, right? Those 2 numbers are not the same. Not even close. The correct way of doing this would be to use scientific notation to get the correct number of sig figs. So if we wanted 3 sig figs here, I'd need to move my decimal back over here, right? Until my number's value is equal between 1 and 10. And then I'd need to count how many spaces I move my decimal point. 1, 2, 3, 4 spaces. So my final answer should be 1.80. And now when we're writing out something in sig figs, right, we always round 1 past. So this 7 is going to make my 0 here round up to a 1. So my final answer should be 1.81 times 10 to the 4th. Hopefully that makes sense for you. All right, and let's try one from the opposite direction to see how it works. If you were given this number, how many sig figs should it have? Take a look. Here's a hint. These right here don't mean anything. Scientific notation is already written to indicate the number of sig figs. So this guy would have 1, 2, 3, 4 sig figs. All right, last step on this one. There are 3 exceptions to sig figs. We call these the 3 C's. These numbers do not have a last decimal or digit that is rounded, so you do not need to apply sig fig rules to them. For instance, counted numbers. If you were to count the number of students in your class, the last decimal or digit of that number, let's say it's 30 or 29, that last decimal or digit is not an estimate. That's a person. There's not going to be like a quarter of a person in the room where you're rounding that last digit. That's a real counted number, something you can see, something you know for sure. So you do not apply sig figs to counted numbers. Number 2, constants. If it's a constant, a number we provide you with, chances are there's more precision or accuracy there than we're giving you. We're probably giving it to you with 3 or 4 sig figs of accuracy, just to make it an easy number to remember. That means you do not allow it to be a determining factor in your number of sig figs. You're going to use your measured values to be your determining factor in your number of sig figs. Finally, the third C is going to be conversion factors. For instance, if we have a conversion factor like 12 inches per foot, okay? Now, 12 inches is technically a measurement, right? But 12 inches per foot is not. 12 inches per foot is the definition of a foot. I mean, we made it equal to 12 inches. That's all there is to it. I mean, if we made it equal to that, then the last digit isn't rounded. It's the definition, okay? It's the same deal if we were to talk about a dozen eggs, right? That is not an estimate. That's the definition of a dozen. Okay, so conversion factors also do not have sig figs applied. Hopefully this system works for you. If not, feel free to check out the other video. In the next video, we're going to talk about how to actually use these in math. So I'll see you then.